Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
This is the podcast where we search for the theories that are going to change the world, and a big piece of that project is searching for a physical basis of fundamental physics, which is really coming out of my mouth feels like a very strange thing to ask for, since presumably physics would be the study of how physical bodies interact to produce phenomena. But it has turned into a very acrobatic mathematical discipline instead. And so lately on the show, this whole past season, we have been exploring ether theories, where ether is the substance that carries the signal of invisible phenomena, such as electricity, magnetism, gravity. It is the stuff underpinning the fields, where fields are kind of these maps of vectors, of potential, of the effects that are felt. And the presumption, going all the way back to the early 19th century and before even, is that there's some sort of invisible substance underlying all of these effects. This idea was discarded at the beginning of the 20th century with the advent of the Michelson-Morley experiments. We're going to talk about that at the beginning of the episode today with our guest, who is presenting a different kind of ether model, different from the elastic ether models we've been exploring this past season.
All previous models that we've encountered on the show have been elastic solids. There's some kind of jello-like matrix that deforms and compresses and rarefies in order to produce everything from charge to gravity. But today we have our first gaseous ether model, and it is presented to us by Dmitrii Osenilo. Dmitrii Osenilo's model is a little bit different. It is a gaseous model, at the heart of which is something that Dmitrii calls ether hydrodynamics. And basically, Dmitrii's argument is the fact that 120 years ago, when mainstream physics abandoned the ether, they had to abandon the ether because they did not have the mathematics of fluid flow that were necessary to actually be able to characterize all of these different phenomena. And so today we unpack why they left it behind, what were the things that were missing, what is the history of fluid dynamics, how ether hydrodynamics kind of came up and out of the 1960s, and how Dmitrii, with his colleagues in Russia, has been working on putting this theory together, running it through the paces, so that he has an explanation for truly everything. There's one thing to note. Dmitrii is a native Russian speaker, and he is explaining his theory in his second language, which is English. And so if you are able to bear with us while we work out some issues with being able to describe highly complicated phenomena of nature in a language that is not your mother tongue, then I think that you will get a tremendous amount out of this conversation, because we really do cover a lot of the deepest mysteries of fundamental physics. And I think of all of the theories that we've come across so far, Dmitrii's might be my favorite. It's got holes in it, like all of them do. I think he recognizes that it has holes and they're still working on it, but I think that it's really worthwhile and I think you're really going to enjoy it.
Remember, guys, this project is only possible because of support from you guys, which means we work directly for you, and it means we don't have to sell any garbage that we didn't make ourselves. We don't make garbage. That's the good news.
I was gonna say.
Yeah, we're not selling garbage, whether we made it or didn't make it. We're not selling anything we didn't make, and actually, we're quite proud of the things that we did make. So we have a line of sportswear. We have a line of gear down in the YouTube shelf. You can check that out. It's on a fourth wall site that'll be listed if you're just listening to this at a podcast location. Few new designs, including the one I'm rocking right now.
The Gothian spectrum.
So, of course, Goethe, this philosopher, poet who played around with light, realized that shadows refracted in a really interesting way that wasn't accounted for by the Newtonian spectrum. So we have made a t-shirt for that. We've got a couple other sweatshirt designs, and we have vinyl records. If you or someone you know collects vinyl records, or if you're just a music enthusiast, this is your chance to get into vinyl records. It's by far and away the coolest way to enjoy music. Not only because it sounds great, but it's also a really concerted and wonderfully relaxing experience. I love the experience of putting on records as I'm working on dinner in the evenings, having that whole half hour of uninterrupted musical experience, including the liminal spaces between, and then flipping the thing over when I'm ready to enjoy the other side. It's a very special experience, and we're super proud of the music that we've made. But you don't have to take our word for it. We are going to play you a little excerpt of it as we lead into today's conversation. You can check it out. If you like it, maybe pick up a record and support the production of our next one.
See you next time.
I met the wandering souls who live like swallows to the caves.
I went to see some people, and I walked down the street, but I got no lack of purpose. And I got no
I think we start at the beginning. I mean, you're a guy who has what sounds like vortex models of almost everything in fundamental physics. So uh, most people probably think that fields are the answer to all of these fundamental physics questions. And they think that the ether is a stupid idea that everybody forgot about 150 years ago, whatever it was, 120 years ago. Why why do people think that? I guess that's a great place to start. You know, everybody has a different perspective on why the ether was rejected. So why do you think the ether was rejected?
First of all, my vortex theory is not love toward vortices, because it's the strict derivation of this theory. And then I understand that vortex is the key to the theory. So the main reason that either doesn't exist for almost everyone is the Michelson-Morley experiments. Everyone knows that they found zero velocity of ether wind. But if we open the paper, we will see that they found either wind velocity maybe 4 or 6 kilometers per second. But they tried to find 30 kilometers per second. And actually, it's not confirmation of there is model, but it's not refusion of this.
I don't even know if everybody knows what the Michelson-Morley experiment is who's listening right now. I think it would be really good to set this up. I mean, the idea was that there's some sort of substance that transmits light and gravity that's in between the obvious objects, right? Like the bodies in the solar system. And this kind of invisible substance should be like this background tapestry upon which everything is moving. And so if you move with respect to it, then you should have some sort of effects on the light signal as it's moving, right? Because the body should be in a different place later, or it should change the speed of the perceived wavelength, or crunch it, or do something, right? And they just weren't able, back in the late 1800s, they weren't able to get any consistent effects out of it. So when you say that they're looking for this wind speed, they're looking for some sort of background motion of this ether with respect to the bodies, right? Is that fair?
Yeah, it's fair.
But you're
Absolutely.
saying that they did detect something. It just wasn't what they predicted that they should detect.
If you are a scientist, you should predict before make an experiment. If you make an experiment without a prediction, you won't obtain any discussable results, because it's not result when you find something and then try to confirm your theory by that. If you are a scientist, you should know what you are looking for.
Wasn't it even worse too, because other people tried to repeat this experiment and got different results? It just seemed like the whole community couldn't really come up with the same results. Like people were seeing
Yeah,
different things. Some, yeah.
Well, it was also a very, very difficult experiment to do, right?
yeah,
So, if I remember correctly, the interferometer that they used was these, so it's like two 90-degree arms that have a beam splitter in them. And so you send a pulse of light into it, and the light goes down both arms, bounces from a mirror at the end, and then returns to the detector, where if the light has traveled exactly the same distance, it will arrive and basically sum back up in exactly the same way that it looked when it left. If the light path that it traveled has changed or been affected by drag, it slows down a little bit on one of the arms, and then you get a little bit of interference in that light.
Gets out of phase, right?
Gets out of phase. But the problem is that they had this like basement apparatus floated on Mercury that was
They're looking for really tiny changes, right?
super tiny changes. And I
Yeah.
think that there is a very long history of people looking for alterations and modifications of the speed
Yeah.
of light and failing to find them and concluding that they aren't there. Like, for a long time, people thought that light didn't have a speed of travel, even. And people argued about this for hundreds of years. They just couldn't do an experiment where light showed up anything less than instantaneously. It just
But
wasn't
it's
possible.
when Michelson and Morley tried to conduct their experiment, they considered that ether is attached to the sun, and the speed of light differs from the one side to another to 30 kilometers per second, because Earth is moving around the sun 30 kilometers per second. So if you measure speed of light this way, forth to the moving of Earth and backwards, then you definitely will find this deviation. But they found just maybe 5 kilometers per second, and precision of their experiment was kind of 5 kilometers per second. That's why almost everyone thinks that they found 0 kilometers per second.
Does that make sense to you?
Which part of it?
Why you would have the expected velocity of the Earth? I'm having a hard time picturing this in my head for
Oh,
some
okay.
reason.
So
Yeah.
basically, why?
Tyler,
Yeah.
just imagine you are staying on the moving car, and you have some wind to your face. Then you rotate yourself, and then you have some either to your back. It will move you back or front. That's how you feel wind.
Do you mean because the Earth is rotating? It will be on my back and on my face? Is that what you mean?
No. Imagine that you're in you're standing in the bed of a pickup truck. Pickup truck is driving, and you're looking front into the direction that you're driving. You experience wind on your face, right? And the direction of the wind is towards you, towards your face. But then if you turn around, the direction of the wind is away from your face.
Yeah, but why these analogies almost never clarify things for me.
Okay.
I don't know why I've turned around unless the Earth is nighttime and I've rotated.
I thought that the angle at which they measured was like in the direction of Earth's travel and then perpendicular to the direction of Earth's travel. And then they swung it and they looked at facing in the opposite direction.
Hmm.
Does that make sense? So basically, if you have a 90-degree angle of
They're kind of assuming the sun is static,
the sun is static, and so you look at
which is weird, but okay.
sure, but you're like looking in the
Yeah, that
direction
makes
of
perfect
Earth's
sense to me.
travel,
Yeah.
okay, and
Yeah.
then you're like, okay,
Actually,
huh?
Charlie noticed a great thing, because there is no reason to think that ether is attached to the sun. But
Right.
in end of 19th century, they thought so. So that's one of the reasons they found maybe almost nothing.
I get it. So they're basically comparing if the sun is the static center, then your distance directly pointed at the sun, that's not going to change too much. But as you're moving into this ether stuff and you measure that length, it should be somehow contracted or squished, or the ether will be compressed or something like that.
This is the best explanation for Michelson-Morley, by the way, that we've gotten yet, because lots of people reference Michelson-Morley, and everybody talks
Yeah.
about the interferometer, but the specific dynamics of why their assumptions were what they were,
Actually, I think
no
it's a
one's
big
mentioned.
problem, because almost everyone doesn't know how to conduct these experiments. Not specific Michelson-Morley, everyone. And maybe the main problem, for example, spin-dependent experiments. No one knows how they are conducted. And everybody thinks that, for example, quantum mechanics is not mechanic theory. I say mechanic by colliding some objects. Quantum mechanics has no collides. It's just probabilities. And no one knows how to conduct spin-dependent experiments. And no one can explain what is spin. it's fun, but it's a problem in fundamental physics, and this problem is one of the reasons why Ether was rejected, because a lot of different phenomena did not have an explanation in mechanical theory, and a lot of different assumptions was maybe kind of speculating, and that's why serious scientists doesn't believe these theories, and now we have real theory.
What are you gonna say,
And
Chef?
that's not all. They had bad models of the ether. For example, they thought it was solid. For example, Lorentz, who made Lorentz transformations, which then was implied to theory of relativity. In original work, they were obtained by Lorentz in solid ether model. And then, for example, Maxwell made their equations using ideal liquid model of ether. And there were a lot of different ether models, but every model explained and reviewed just specific cases of phenomena. That's why they have no unified theory.
You mean that each person was only addressing individual phenomena, like
Yeah.
Maxwell was just doing electricity or magnetism, and so you had to cobble together. Sometimes the solid worked, sometimes the fluid worked, but nobody had
Yeah.
an overall picture of what was happening.
Yeah. Sometimes something worked, and you don't know which properties you can define, because experiments, for example, of with charge defines charge divided by mass, not charge, not mass, but only charge divided by mass.
What Dima's pointing to is that if you look at the experiments like the cathode ray tubes that discover the free particle of the electron, they don't discover an individual particle. They discover some kind of event that occurs inside of the detector that appears to have a mass to charge ratio, because they have to measure both of these things at once and they can't get a discrete value for either one. And even the Millikan oil drop experiment, in some ways, it does derive the mass of the charge, but it is still kind of this like ratiometric thing of, you
Plus,
know,
the word mass is weird all of a sudden, which is really just this momentum quality of like deflecting this beam thingy.
yeah.
And in so much as the concept of mass is applied to inertia.
Yeah, because like in the cathode ray tube experiments, mass is derived from how much a beam curves under the influence of a magnetic field.
Yeah. It's almost like I often think like if you had a guitar string and you push on it really hard, like say you
Yeah.
tune up a guitar, it's really tight thing. If you push on it, you feel a lot of mass, right? It's really tension in the string
Yeah.
is what you're feeling, but it would be easy to just say I'm pushing 40 pounds, or a bow, like a bow that you shoot is the same thing. It's like
Yeah.
40 pounds to displace that string, but the string doesn't actually weigh 40 pounds. That's insane. It's just the tension equivalent of displacement.
So the weird thing is about all of the cathode ray experiments is that they showed extraordinarily light particles. So it wasn't, and I think that the tension model, if you're saying that, okay, so there's this thing that extends from electrode to electrode and it's under some kind of tension, and that's where the mass comes from, then you're stuck with the fact of like, well, it's really light.
That's fine.
Yeah. So I
I
think,
mean, my point isn't really to like nitpick about the momentum, like the experimental results. I'm just saying that the concept of mass in terms of being a gravitational phenomenon gets tricky when some sort of material is under tension, because you have a really hard time talking. It's not an inertial thing at that point. Like the bowstring, it doesn't weigh 40 pounds.
I guess what I'm trying to say is that if we're talking about the discovery of these subatomic units that we can only understand ratios of mass
Yeah.
to charge, what is difficult to parse at that point is what does it mean for something like an electron to have mass without a physical theory for mass except for electron volts and like magnetic moment, and like these are not conventional massy qualities, is I guess the point.
I need to notice that in every experiment, you have a lot of paradigm load of scientists. Because, for example, if you want to consider some experiment as a relativity effect, then you should just believe that speed of light is constant. But if you want to consider it by hydrodynamics effect, then you can not believe this, because speed of light is pretty constant thing, but it's not constant. Maybe 5 kilometers per second, more or less, it's okay for hydrodynamics. And for example, Miller did experiments where he found 10 kilometers per second speed of light deviation, but he was on a mountain. That's why he had high results.
What's special? Why? That's
Why?
crazy. Yeah. What's the mountain have to do with anything? It's rare.
Actually, ether is partially entrained by matter, by substance. And when you are staying on the surface of Earth, then ether entrained much more relative to the Earth. Speed of ether will be almost zero. This is one of the reasons the speed of ether is much lower than they predicted.
So you're saying that the ether is moving more separately from the Earth the further away from it you are. So you would
Yeah,
detect
yeah,
more of a difference
of
out
course.
there. Okay.
If you will try to measure either speed, maybe 1,000 kilometers away from the Earth, you will find 30 kilometers per second, I'm pretty sure.
We've been looking for ideas for satellites.
We just need to conduct these experiments. And maybe in theory of relativity, it's not really time dilation, because if you use Lorentz transformations, you will receive some dependence of time and speed. Not because time is dependent to speed, but because you have an equation which links these two values. And you may, in theory of relativity, interpret this as a time dilation. In hydrodynamics, you will interpret this as just speed of light deviations or density deviations or something like that.
Did that make sense to you?
It made sense to me in the 30,000-foot view, which is that the mathematics that you use deeply inform the interpretation that you make. And so in special relativity, you have that there's time dilation that accounts for differences in speed, but in ether dynamics, the mathematics that has the same sort of effects tells you that it's not time dilation, it's literally the speed of light is changing. So
Okay.
it's like it's not time squishing, it's
Yeah.
the speed
I
of
see.
light
I see.
changing.
Right on.
Actually, when we're trying to make a theory, we have to make some assumptions before we make a theory, because we need some terms, we need some rules how to play this game. And when you try to make a good theory, you make just obvious assumptions, which are not contradicting to your common sense, which are observable, which are okay for everyone, almost everyone. And if you want to be a maybe smart scientist, you will say that, okay, we have space-time curvature, and you have some probability of nature or something like that. It cannot be imagined, because it's, may I say, bullshit word. But but if you make space-time curvature assumptions, you cannot measure it, because you are inventing new term that has no analogy, that has no understandable things inside it.
I'm always talking about this, which is that a theory is dependent upon the metaphysics that go into constructing it. Any story that we tell about the world is foundationally metaphysical. What it,
This is one of your controversial takes on a word.
yes.
Yeah, it's funny because Nastya always used to make fun of me for bending words into new things, but now she's the queen of it. So, by metaphysics, you mean the assumptions you bring to the table without even realizing it for the most part, right?
They're the rules by which you think the universe works.
Yeah.
Like,
Is there a
there's
God? Isn't there a God? Is there a beginning of the universe? Isn't there a beginning of the universe? Do things have to have mechanical basis, or can things just be magical and weird at the fundamental scale? These are all metaphysical baggage that you bring to an argument.
Yeah, and so like the difference between, say, Lord of the Rings and Star Trek comes down to the metaphysics that the story was built from. Like, one is a metaphysical world of dragons and magic and sorcerers and rings of power. The other, did I say Star Trek or Star
You
Wars?
said Shrek.
Okay, and the other one is like phasers and Borg and USS Enterprise. Like,
But they're both quite magical, right?
yes, but the rules by which the magic works are different. And that set of rules, the things that you say, like, these things are allowed, and these are the rules by which they can happen. That's the metaphysics.
Right, like Captain Kirk doesn't whip out a magic wand and turn somebody into a toad or something.
Exactly, but he does have a magic wand, and it's called his, like, transponder
But it only
or
does the
whatever.
transpondery thing, right?
Exactly,
Yeah.
it's a magic wand
Okay.
that has rules,
Right
and
on,
those
I love
rules are
that.
the
Yeah.
metaphysics. And so what Dima is saying is he's like, your physics, your science has these things that go into it. And so if you tell yourself, okay, well, you can have time dilation, you can have space-time as an object that you can't possibly measure
Or imagine.
or even imagine, then you are stuck with one set of outcomes. But if you make different demands of your scientific theories, then you have a different world
Yeah.
with the exact same starting point.
Actually, one of the rule of quantum mechanics is incomprehensibility of nature. So
Mm.
they basically say that there is no rules. And there were a lot of different times when they say, for example, energy conservation law doesn't work.
Mm.
And it doesn't work in theory of relativity, and it doesn't work in quantum mechanics. Locally, it doesn't work, but or opposite, I guess.
No, I think it's locally. I think you're pointing to, are you pointing to like when Bohr comes up with this like orbital model where he's like, they have special orbits where they don't decay into
Yeah.
the nucleus?
That's one of the assumptions that it leads from nothing. We have some experiments, it's phenomenology, but we have no mechanism of this. And hydrodynamics provides this mechanism. So the most advanced of hydrodynamics that it doesn't refutes experiments that we are observing. Hydrodynamics gives a basis, mechanical basis of almost every experiment. The main law of hydrodynamics that nature is understandable.
Isn't that crazy that the metaphysics of nature should make sense is a minority position in fundamental physics? Like it's really shocking to me. Like I have a hard time believing that this is true, but every time that I hang out with an academic fundamental physicist, they always confirm the reality, which is that they truly do believe that
Mhm.
crazy stuff that can't be understood and doesn't make sense is happening somewhere in the universe, like at
Yeah,
scale, at a small scale. And I always try so hard to give them the benefit of the doubt, and I try to really like think, well, maybe you don't really think that, maybe, but they really do think that. It's so wild
yeah,
that that's kind of the standard approach of these people who are, some of the smartest mathematicians in the world today. I don't
yeah.
know. Anyways, I don't have anything else to say. I
Actually,
just think it's crazy. Yeah.
I think they think that nature is mathematics, and it's not. Mathematics is just a tool to describe a nature.
That's just
It's
like your metaphysics, man.
Is there any other situation where people mistake their tools for reality? Is there like any other place in the universe where people confuse a tool for reality? Like, does anybody think their guitar is a piece of music or something? Do you know what I mean? Like, is that a thing that happens anywhere other than with mathematics? It's so bananas. Anyways, I'm not trying to. This is one of my topics I just get off on. Uh, but yeah, let's keep going. It's fine. If you think of something, I would love to hear it. Maybe people in the audience will comment on this. Where are tools mistaken for reality other than mathematics?
Yeah, I don't think that there are. I mean, in general, I think belief systems do that. Like, right? Like if you believe in if you believe in something, that's a story. you come
Actually,
to.
it's not a science when you believe in something.
Agreed.
It's just your maybe religion, but I'm not playing against religion because religion makes a different role in human's life.
Mm.
But it's not science. It's not nature understanding. It's another thing. And if we want to do science, we want to believe in something. We just need to make an assumption and try to refute it or to confirm this.
Pardon the interruption, but I have to ask you for a favor. If you were listening to this podcast and you were enjoying it and you want to see more of these ideas in the world and you want to power our ability to explore these ideas in person, to bring listeners together for in-person events, then consider coming over to patreon.com/DemystifySci. For 75 cents a week, you will spare us forever the indignity of having to hawk cheap trinkets on the internet in order to support our podcast. So come over today to patreon.com/DemystifySci and support what you love.
And that's how Hydrodynamics was built.
Should we tell people what Aether Dynamics is?
I think we're still trying to.
Shiloh's manning the outline.
Yeah, I'm following this outline we made up. So, or you made up. I did nothing. I think we should finish up. Have we talked about all of the requirements for a usable theory? I mean, obviously it should be knowable. I like that a lot. What are we missing? What else should a really good theory contain?
If the nature is understandable, then we have some methods to understand it. And when you measure something in experiment, you measure changes of place in time, in space. Matter is kilograms, space is meters, and time is seconds. So everything can be described by these three things. And there is no electricity, there is no something weird like quantum mechanics probability. That's just mechanic things. And that's why we can describe every phenomena with mechanics. And that's the second thing we should assume to build a good theory. First of all, it's understandable. Second, it's understandable by mechanics. And if you have mechanics, then you have math apparatus, you have imaginable models, you have tools, you have everything. And you should believe in experimental data, not in thoughts of some genius people, just experimental data.
Makes sense to me. I mean, it's seems like you should at least give it a try, right? I think that's if I see no reason to look around the room, study the physics of how things move on my table and all of this, and understand the mechanical world really, really well, and then to look at these scales that we can't quite probe with technology, down below the scale of the atom, and then assume that for some reason things just work differently. Like, that's very, very strange. I understand that the pressures might be scaled differently, but at the end of the day, it's like everything in the room basically works by displacement. And I think that's what you mean by mechanics. It's like stuff pushes other stuff out of the way. I mean, that's a pretty simple set of rules to comprehend.
It's
like
it's
you could
obvious, almost obvious, self-evident, and that's what I'm talking about when I say that you have not postulates, just obvious assumptions, and that's the basis of hydrodynamics.
I think that's a good place to start building a theory, because we should at least make sure that we've exhausted that possibility before we start speculating the unknowability of nature. I feel like we gave up too quick.
We have some problems with this approach. Had some problems in starting of 20th century because we have no computers, for example. We could not model everything. Actually, we can't model, for example, toroidal vortex or viscous gas today because it's too complex task for even supercomputers. But we have a lot of experimental and model data of flows in liquids, in gases, in different types of matter. And we have a lot of experimental results. For example, we have quantized circulation in superliquid fluids. And we had no these experiments in the start of 20th century. And we have no reference of charges. And now we know charges are quantized. And circulation in superfluid liquids are quantized. So we can put it one to one and compare.
I like that. So you're basically saying we didn't have access to these new ways of analyzing phenomena that we have now. We didn't have the computational power back then. And I think that's kind of how the tragedy unfolds, is that they're not able to discern these tiny differences. Their analytic powers are not as strong as they are today, of course. And they perhaps didn't even, like, whole fields of science, right? We're going to talk about different fields of hydrodynamics and all this. I mean, like you said, even vortexes today are still difficult to calculate with huge computers. I mean, these poor 1800s guys with their, I don't know, slide rulers or whatever they were using back then, their abacuses.
That's not all. Prandtl has published his work in 1904 year.
Wait, who is this?
Prandtl may be the main person of 20th century of hydrodynamics. He introduced a boundary layer theory, and scientists of that time have no time, have no tools to even apply this theory to their works, because it have been just published, and that was only 8 pages paper, and it has been developed much later. Maybe in the middle of 20th century, we have enough hydrodynamics.
So Prandtl was what, in the 1930s, 1940s?
Didn't it say 1904?
1904.
I'm confused now. I thought we were talking about people not having the tools.
What Dima's saying is he's like, Prandtl published this paper, but it wasn't folded into any kind of theories at the time, because I was going to ask you, what was the contents of the paper? Did he propose some kind of mathematical theorem?
He proposed boundary layer. You can divide the task you are solving by boundary layer when you have to consider viscosity and the rest part of medium, when you can omit viscosity. And it simplified every hydrodynamic task much more. That's not all, because you have to linearize some equations. You have to make more assumptions, which you can obtain from experiments which were not conducted at that time.
So basically, the idea is that like each system in which you are working, each system that you study, you have to have particular mathematics for it. Like that's just the nature of it. Because if you're dealing with physical systems, the mathematics that you use to describe them have to encompass some insane physical configuration, and that's difficult to come to.
Hydrodynamics is pretty complex thing, and almost everywhere except of laminar flows, common logic doesn't work before you understand how it works. For example, we have Magnus effect, and for example, you have a rotating ball, and it goes forward, and it rotates that way. So here you have resistance of the air, and it pushes this ball aside. So this behavior is like charge behavior, for example, Lorentz force. Absolutely the same behavior. And that is one of analogies I have in starting of developing my theory. And when I found this, when I tried to mathematically describe these phenomena, I've found a lot of things that helped me to develop electrodynamic theory as a hydrodynamics theory. And then I had strict derivation of Maxwell's equations by using just hydrodynamic equations with no uncommon assumptions. It's pure maths and logic, nothing else.
All right, we'll get to your theory, but I don't think we're quite ready yet. We need to pull out the. First of all, we were just talking about why the early scientists studying the ether gave up. We started talking about what they should come to expect. Now we're kind of mixing the two together.
Well, I think that the idea is that people gave up because they didn't have the mathematical tools to be able to study it. Like you have Lorentz even in his Nobel speech, which he gets, I think, like 1903, 1904, maybe 1907. I don't remember when he got his Nobel. But in his speech, he's talking about, the electrons being like little vortices. This is a thing that he maintains for a long time when he talks
Yeah.
about trying to figure out. So the Zeeman effect is this well-known effect that was first discovered in, I think, like 1897, where you can put atomic spectra, you can put atoms that are producing light into a magnetic field, and it changes their spectra. And everybody had to figure out how that was possible. And Lorentz had this kind of like preliminary hydrodynamic version where he's like, okay, so there's
Yeah.
like angular momentum of the electron vortices, and when you put them into the magnetic fields, they respond differentially, and so that's why you get the splitting of some lines into two, and some of them split into. He had a physical model for it,
Yeah,
and
that was just speculations of
yes,
at the time, and now we can
absolutely.
calculate this
But
most part of
it-
this.
that's pretty cool. So, but I think that what Dima is saying is he's like the tools just weren't there, and so even when Prandtl publishes his boundary layer theory,
Yeah.
does it just disappear and is not paid attention to because it's too early, or is it just applied to hydrodynamics while the field of fundamental physics goes in a different direction? Like what
Uh,
happens there?
Actually, when you publish something, it cannot be applied to other works because you have to understand it. You have to try to apply to your theory, and maybe after a few years, you will receive some combined results of this theory and your theory, and you should live with this for a couple of years, and then you will have result. So if Prandtl published it in 1904 and you received it maybe from someone else in 1907, and you have to work with it maybe 3 years, and only in 1910 you will receive some results. And actually, maybe in this time, some results started to be created from someone.
If people had applied Prandtl's theory and understanding of this boundary layer separation business,
Mm.
would they have been able to explain the ether results better?
Yes, they can, and but that's not all, because you have to calculate viscosity and a lot of complex phenomena, and you have to have some computational powers. You have to use some new experimental data just to make an assumption, because you don't know what to assume. What to assume?
What to assume. You got it. I like that though.
Yeah,
What to
what to
assume.
assume.
Indeed.
It's actually much better. What to assumped. I like that.
So yeah, they don't know what conditions to put into these equations, even if they were to use the equations, which they didn't know about anyways.
What?
I think I'm with you, man. It's okay. All right. So, uh, okay. So, how to build a theory? Um,
Well, we have that it has to be understandable. It has to be mechanical, and it
Yeah.
has to have experimental data that it agrees with.
Yeah, and then we were should to use this experimental data to make good assumptions and derive your theory from these assumptions, from these experimental data, from these mathematics and others. So we have mechanics. We have mechanical models for gases, for liquids, for solid bodies. We have a lot of different mathematical models, and we know that bodies does not have resistance while moving in a vacuum. So we have really small or even zero resistance in vacuum, and that's first thing. Second one, we have really fast waves in ether or vacuum or kind of this. And we have different densities For example, we have particles which density is maybe 10 in 17th orders of magnitude. We have almost zero density of free space, and the only model which can handle all of this is gas, because everything else resists to motion.
Are you saying gas like GAS, like gaseous? Is that the word?
Gaseous, like air,
Like air. I see. I see.
model.
Okay.
Gas. How?
Oh, you just sorry. I was looking on your outline here. There's just this word GAZ. I didn't know if that was.
In Russian, it's gaz.
I see. I see. Yeah. Okay. Cool.
What's
So-
correct pronunciation of this?
Gas.
No, you're doing it right. I just
Yes.
I wasn't sure if that was something that some particular technical term that I
No.
didn't understand or something. So you're saying that it has to be the ether. You're looking at candidates for
Yeah,
the substance of the ether, and you're making an argument for why it should be this diffuse particle system, essentially.
Yeah.
Okay.
Next thing we
Wait. Can you sell me on that a little harder? Because I'm not totally sold on that yet. Why do you think that it has to be a gaseous particle system, as opposed to we've had a lot of ether theorists on this season talking about elastic solids, for instance, right? What else have we seen? Yep, that's about it. But
Okay.
different flavors of that, right? So
it's-
why do you choose a gas versus an elastic solid?
Actually, we cannot move through the solid body. For example, it's.
Oh, I forgot about fluids also. We could talk about why not fluids also. Fluids, solids, and gases.
Fluids has surface forces, but we don't observe it. We don't observe fissures in a space. We have compression of ether if we assume that the ether exists.
So Dima's making the same argument that you always make, which is the fact that like waves travel on surfaces in liquids. And so if you don't have he's saying like you don't have fissures.
He's also saying fluids aren't compressible.
Also something that you say all the time. And so basically like you can't have a fluid theory because that doesn't match the data.
It's not a big difference between the gases and fluids, but we can assume that this is a liquid. Maxwell did the same assumption, and he derived his Maxwell's equations, not strictly, but partly phenomenologically, but he derived it. And it's good too, but it's not good enough. It's not good as gas model. And I will say why next.
I don't think we should move on from the elastic solids just yet either, because I think your only response was that you can't move in an elastic solid, but I think
it's not the only. But for example, we have some transverse waves, and in the solid body we have transverse waves only in a surface, only in fissures, on layers, on something like that. If you read seismology literature, on every page you will find a surface, layer, boundary, fissure, or something like that. Words which are synonyms to surface. And if you have no surfaces, you have no transverse waves. And we have transverse waves. It's a little speculative because almost everyone thinks that transverse waves exist in solid bodies, but there is no mechanism for this. You cannot show how they work, because if you have layers, you have surfaces, you can show this. Or if you have one-dimensional model, you can show this. But if you have endless body with no surfaces, you can't show this.
it gets really difficult with these elastic solid type theorists because they don't imagine that there are bodies at all. They imagine that the bodies we perceive are defects in some large-scale homogeneous lattice, right? And so there's the appearance of bodies and the appearance of surfaces, but they're really just wave boundaries. And it's maybe not fair to say that they don't have the ability to generate transverse waves because they don't have surfaces, because they think that surfaces are a phenomenological illusion, essentially. And so
yeah, you are talking about, I guess, standing waves as
surface boundaries, something like that.
Yeah,
I think I'm just trying to represent their opinion as best as I can. Yeah.
I understand. you need a surface to have a standing wave, because this standing wave need to reflect from something, and you have to have this boundary that will reflect a wave which goes here. And if you have no boundary, you cannot obtain standing wave.
So I think that the way that an elastic etherist would make this case is as follows. So the ether is an elastic substance that is capable of densifying and rarefying,
Yeah.
and the subunits are capable of movement. And so, if we're talking about, let's say, a standing wave, then I think that the boundary inside of the elastic ether would be something that was sufficiently dense that could act as a reflector. So,
Okay. How can we receive dense deviation in a solid body with no other forces?
well, that's you kind of require like a prime mover that creates the densification in the first place. But I think that this is in some ways the problem with all physical theories, which is okay, well, how do you get atoms in the first place? Like, there is just some set of objects, and those
Yeah.
objects are producing things that appear like boundaries and things that appear like waves because they push and pull on the
Yeah.
substance of the ether. And so when
Understand.
Shiloh's talking about waves, literally, like what they mean is that if you take the entire substance of the universe to be a three-dimensional grid
Like
that is
Jello.
like jello that's
Yeah.
squishy, you just get this. The wave is the process of things getting squished up and then getting squished down and then getting squished up. Like the
Yeah.
wave is the traveling front of that motion for them. Is that? Do you
But
think that's
if
fair?
you will push this point upper, then the point above
Above it.
this will receive much more interaction than those points which are side by side. And the main part of energy will go up, not to sides. And if you try to calculate this, you will receive this, because transverse waves
I think that
fade
would.
out much faster.
I think I would love to have bring you on to debate one of these elastic ether
Dmitrii
people,
versus Chantal
because
Roth.
I'm not capable of defending their position. I think fair. I can't do it as well as they could.
Okay.
We're meeting. I think we're doing another one not tomorrow or the next day with this
Angular momentum theory of everything.
mathematician dude,
Yes.
yeah, who has a somewhat adjacent elastic ether. I think you guys are both right, personally. But you're both, yeah. I think that there's some overlap here that's kind of interesting. But we can move on, because
So
it would be
basically,
good to have you.
can we explain to people why transverse waves are so important? Like, assume that somebody knows that waves are important, but like, why the hell transverse waves?
It exists. And we should to describe this. And if we won't describe this, so it's not a theory, it's just a kind of theory.
Well, light is a transverse wave. I think that that's why it's so important.
For example, electricity is transverse waves. There are a lot of transverse effects.
And so, if you propose a medium that cannot
Yeah.
produce a transverse wave, which is, it's weird, right? Because it oscillates in one axis, it oscillates in the other axis, and then it also has net forward momentum.
That's the longitudinal component of the wavefront. The transverse is literally just orthogonal to the direction of propagation. And the only time that we ever, like at the beginning of the conversation, we said it'd be nice if we could look around the room, understand the physics of the world around us, and then apply it to the fundamental questions. And the annoying thing is, if you want to look for transverse waves in your local environment, there's really only one place to see it, or maybe two in our house. But one is, the main one is at the surface of ponds, right?
Where's the second place in our
Oh,
house?
the guitars. Yeah, it's hard to find examples, right?
Guitar string is purely surface. That's why transverse waves are moving on a guitar string.
Fair enough, man. But if I'm just saying, it's hard for people to find examples, I think, of transverse waves in their
It's
mind, right? It's just not something that makes a lot of sense otherwise.
I will
actually
put a picture of transverse wave in here.
uh,
Transverse wave.
the dynamics says that there is no transverse waves. Maybe in what I want to say, in for example, water, you have surface looks like transverse waves, but if you will see under the water, you will see vortexes are rotating on near the surface, and there are a lot of different phenomena that looks like transverse waves when you try to measure it. But it's not purely transverse waves. It's vortex phenomena which can be considered as a transverse wave.
Mm-mm. That's a funny noise I made. Yeah, it's funny because if you look at like a dipole antenna, right, and people are probably uncomfortable with thinking about antennas as emitting light, but they are. They actually make these little vortices as these waves proceed outward. If you look at
Yeah,
the
yeah, it's
propagation, it's kind of
There's even
interesting.
one crazier thing about antennas is that as you
Yes. Sorry.
certain types of antennas produce distribution patterns that look
yeah.
almost identical to orbitals.
That is true.
Like electron orbitals and the pattern of radiation that emerges from antennas as a function of their geometry overlap in striking ways sometimes.
They're like spherical harmonics, right, or something like that.
They're toroidal. Like there's one that I saw the other day that there's an antenna design that looks exactly like, I think it's the F orbital.
But that's a spherical harmonic also. The
That
Yeah.
torus is a
yeah.
spherical
Okay, fair.
harmonic.
All spherical
Actually, in
harmonics.
the dynamics, electromagnetic waves are different types of flow constructions in either, and it can be different shapes.
All right, we're gonna get to your theory. I promise you. Let's check in on the existing theories. How does this relate to existing theories? Quantum mechanics, relativity,
Yeah,
electromagnetism.
maybe last half of year I derived known mathematical formulas from hydrodynamics to explain, for example, quantum mechanics. First of all, I want to say that light polarization can be modeled strictly from vortex dynamics. We can imagine that light is a vortex, just a circle vortex, and we can write a motion equation of a particle on this circle. And if we consider this particle in one time and after a quarter of period, and we will write it in complex form with imaginary numbers, then we will obtain absolutely identical to John's formalism or quantum mechanics math apparatus. So everything that can be observed in polarization phenomenon, it can be explained by quantum mechanics, can be explained by hydrodynamics absolutely the same way, but with the imaginable model. Just circle vortex, which is rotating in different directions.
Hmm.
And it's maybe the first time in history when someone made one of quantum effects imaginable. But that's not all. For example, the last work I did maybe a week ago, I've found a way to describe spin phenomena. Spin phenomena is calculated by quaternions, which are pretty complex form of imaginary numbers. And they describes rotational effects in space. And when we consider electron as a vortex, a toroidal vortex with a complex internal structure, then we will find the same mathematics that are used in quantum mechanics. So we can derive spin directly from vortex dynamics. Just it's pretty complex thing. It's topology and it's quaternions, for example. It's not a lot of people understand how it works, but it works and it can be imagined now. just as flows in vortex particles.
Well, so I feel like we're getting into your model right now. Is that where we want to be in this? Are we finished setting the stage? Do you feel like we're ready to really get down to?
We should notice one more thing. We said that ether is is gas. How can be constructed? Particles can be constructed, and there is only one way, because the only mode of motion in gas is which can localize some matter, dense matter in small volume, is toroidal vortex. It's the only one, and that's why we should consider particles as toroidal vortices. And if we have particles as toroidal vortices, which are rotating fast and have some viscosity or different properties, then we should consider fields as something that happens around a toroidal vortex. And that's the basis which we can use to start to develop mathematical and mechanical models of every phenomenon.
That's it for part 1. Stay tuned for part 2, where we will be going over the specifics of Dmitrii's model of light, electricity, magnetism, and gravity. If you've made it this far in the conversation, there will be a link that shows on the end screen, or you can find the link to part 2 in the description. See you